Hello and welcome back to another session of TAE certification training. In today's session, we will go through the final topic of Chapter 3, which is support for a variety of target systems. So let's get started. So let's start with the definition of TAS support. TAS support for a variety of target systems refers to the ability of a TAS to test different configurations of a software product. It means that a test automation solution has the capability to test different configurations or versions of a software product effectively. So these configurations may include variations in software components, environments, technologies, or tools, and the TAS is designed to handle and automate testing across this diverse range of configurations, ensuring comprehensive test coverage. So throughout today's session, we will use this example scenario. So let's imagine a software company is developing a weather forecast application. This application provides weather updates to users and utilizes various software components and configurations. Okay, so as you can see that in the definition of TA support above, different configurations is underlined. It's because there are several factors that can affect the configuration of the software product that needs to be tested, and this is what we will explore in the next slide. Different configurations refer to any of the following, and the first one is number and interconnection of SUT components. Okay, so going back to our weather forecast example, let's say that one version of the application, version 1.0, is designed to have a basic structure with essential components, which are data retrieval, data processing, and user interface. And in a newer version, 1.1, the application has an expanded feature set with additional components like real-time radar tracking and user customizable alerts. So the degree of interconnection between these components varies. So for instance, the data retrieval component may have different APIs for accessing weather data, and the data processing component may need to handle diverse data formats. All right, so the second point is environments, both software and hardware on which the SUT components run. So the software can be deployed in multiple environments, such as cloud-based servers, or it can be on-premises data centers. So different clients may choose various hosting options, impacting the performance, scalability, and reliability of the application. Over here, the choice of hardware also matters. So some clients may opt for high performance servers, while others will go for reliable options. As for example, the data centers, they have backup systems and failover mechanisms, reducing the risk of downtime. Next, we have technologies, programming languages, or operating systems used to implement the SUT components. Okay, so the application may be built using different technologies and programming languages. For instance, one version might be developed using Java, while another uses Python. Similarly, operating system compatibility is also very crucial. So some clients prefer a Linux-based server environment, while others opt for Windows. Number 4, libraries and packages the SUT components are using. Okay, so in this table, if we look at the first column lists the specific software components within the SUT. Then the second column specifies the libraries/packages used for each component in version 1.0 of the application. Then the third column specifies the libraries/packages used for each component in version 1.1 of the application. And in the fourth column outlines how the choice of libraries and packages impacts the application for both versions. Okay, so various libraries and packages may be used for specific functionalities. For example, one version of the application might use a third-party library for geolocation services, while another integrates a custom solution. So the choice of packages can impact the application's features, performance, and also resource consumption. And the fifth and last one is tools used to implement the SUT components. The tools mentioned here are the software development tools, programming languages, and frameworks used by developers to create the various components of the weather forecast application. For instance, the data retrieval component might be developed using Python, while the data processing is using Java, and the user interface component might be built using JavaScript and a specific framework like React. While the first four aspects impact the TAS on any test level, the last one applies mainly to component level and integration level testing. Okay, let's have a look in detail in the next slide. Okay, different levels of testing, we already covered this in the foundation syllabus, but just to recap on the component level and integration level testing, component testing level focuses on testing individual software components to ensure that they function correctly. So the tools used for implementing these components impact how they can be tested. For example, if a specific tool was used to implement the real-time radar tracking component, the TAS needs to work with that tool to verify its functionality. And this means that the TAS must be compatible with the development tools used for different components. Similarly, integration level testing assesses how different components interact and whether they maintain data consistency and functionality when combined. And the tools and technologies used for component integration are critical over here. So for instance, different versions of the application rely on different technologies. For example, one uses Java and other uses Python. So in this case, the TAS must be capable of interacting with both technologies to ensure seamless integration. Next, we have defining and implementing TAS capabilities. The ability of a TAS to test different software product configurations is determined when the TAA is defined. Okay, so in the context of the weather forecast application, this means that during the initial planning and design phase, the TAS capabilities must be considered. For example, when designing the TAA for the weather forecast application, the development and testing teams need to decide whether the TAS should be capable of testing both Java-based and Python-based versions of the software, as well as handling different components and environments. Next we have, however, the TAS has to implement the ability to handle the technical variance. So while TAS capabilities are defined in the TAA, the TAS itself must be implemented to handle the technical variance among different software product configurations. So in our example, the TAS needs to be built in a way that allows it to interact with components written in Java or Python and work with various databases, web servers, and operating systems. It should be flexible enough to accommodate these technical differences. And the third one is has to enable the management of the TAS features and components needed for different configurations of a software product. So this involves maintaining and updating the TAS to ensure it aligns with the evolving software configurations. And in the context of the weather forecast application, as new components are added or existing ones are modified, the TAS should be updated to accommodate these changes. Next, we have managing TAS variability. The handling of the TAS variety in relation to the variety of the software product can be dealt with differently. It means that handling the variety in the TAS in relation to the variety of the software product can be approached differently. And over here, two specific approaches are mentioned. The first one is Version configuration management for the TAS and SUT can be used to provide the respective versions and configurations of the TAS and SUT that fit to each other. This approach involves maintaining different versions and configurations of both the TAS and the SUT that are known to work together. For instance, if there are multiple versions of the weather forecast application, there should be corresponding TAS configurations for each version. Next one is TAS parameterization can be used to adjust a TAS to an SUT configuration. TAS parameterization means that the TAS can be adjusted or configured to match the specific configuration of the SUT being tested. In our example, if a client uses a unique database systems, the TAS can be parameterized to interact with that database. And the last section is continuous consideration. It says that it is important to note that while design for TAS variability is mainly a matter for the TAA, the maintenance of and improvements for variability are a concern throughout the TAS lifecycle. It requires continuous consideration and efforts to revise, add, and even remove options and forms of variability. Okay, so over here, design for TAS variability means creating the test automation solution to handle different versions or configuration of the application, like regional variations. Then we have maintenance and continuous improvement over here, which involves adapting the TAS to evolving versions, technologies, and requirements over time, ensuring it remains effective in testing. For example, as the weather forecast application adds new regional versions and data sources, the TAS must be designed initially to accommodate them and continuously improved to adapt to changing conditions and technologies. Finally, we have covered Chapter 3 on the generic test automation architecture. In our next session, we will proceed to work through a set of practice questions. Until then, happy testing.